So good morning or good afternoon, depending on where you're calling from. My name is Charla, and I want to welcome you to today's Tech Talk, streaming in the world of legacy applications. Before we begin, we have a couple of housekeeping items to go over. Everyone will be muted for the Tech Talk, but please type any questions you may have as we go along into the Q&A panel. We'll try and stop frequently to answer those as we go along, as well as answer them at the end of the presentation. Also, this Tech Talk is being recorded and will be sent to everyone via email following the talk. Now that we've taken care of that, let's go ahead and get started. Today's Tech Talk will be presented by Vladimir Schreiner and Joseph Bartok. Vladimir is a technical product manager for Hazelcast with an engineering background, master's degree in computer science, and deep expertise in stream processing and real-time data pipelines. Vladimir joined Hazelcast in 2016, and he is the product guy behind the Hazelcast Jet streaming engine. He will be joined today by Joseph Bartok. Joseph is a Hazelcast Jet software engineer. He has been a Java developer for 16 years now. The first 10 were spent on various proprietary real-time market data systems in the financial industry. Later, he got involved with ultra-low latency Java applications. He's currently working with Hazelcast on the stream processing product called Jet, and he's more and more involved with this interesting domain of processing global scale infinite data sets. With that, I'm going to pass it off to you, Vladimir, to get us started.
Okay, thank you, Charla. So we have a lot of experience here. Let's get started. To emphasize one thing that Charla said, one of the motivations to actually do this technical talk was to somehow bridge this period with lack of meetups, basically with no meetups. So I would like to encourage you to ask questions to make it as interactive as possible. I will try to stop once in a while, check questions and answer those. So just please do. Otherwise, it would be just me doing the talking. So today we're going to talk basically about how to enable streaming with legacy applications. I will start with setting up a scene a little bit. So let's actually talk about what I see under legacy apps, because that can mean many things. There are a few approaches that can be used, some of them more fancy, some of them more traditional. So let's discuss those, and let's actually pick one and elaborate how a possible solution using this approach could look like. So to start with, what is a legacy system, right? I come from an enterprise software engineering background, work for telco and government. So I have my own opinion to you of what legacy is. I did some Googling to make it a little bit more objective, but it mostly overlaps. So it's a software with no documentation. So knowledge just isn't recorded. Original devs are gone. If you want to add something, you have to basically reverse engineer everything to understand all the hacks that were made to the software at the time of its creation. Usually there are zero automated tests. You usually have like high-level manual test cases and a team of QA people just doing those test cases manually, but there is no automation. And with basically any change, there is a high likelihood to cause some kind of regression. So any change is basically finger crossed to not mess it up too much. There is actually nice literature about how to approach legacy applications, and the approach is always try to add tests, but how to add the tests to the code that wasn't written as testable, right? So it's a tricky thing to do. The rule of the thumb is that you are trying to change the code base with a low or minimal risk. Another frequent thing, and I would use this as prerequisite, is that legacy apps are usually built around a core relational database. So how that works? Each app usually has an internal state, and you can trigger an external action to basically change the state. So you have something like a REST API or a web app interwoven with application like business code, so that you can click on a button and the state of the application changes. And the state change is immediately persisted in a relational database. So the application itself is kind of black boxed. There are no easy integration points apart from this Web UI or REST API. The thing is that such an application just works. It's too expensive or too risky to just pay the technical debt and adding all the documentation, adding the tests, maybe increasing the amount of integration points, right? Usually the legacy applications are growing or have been growing for years, and just a single business case doesn't fit to the current technical solution, just doesn't justify changing it completely. So you may say, okay, for greenfield projects or for companies that are tech innovators, so they are willing to pay a lot to paying a technical debt, that's easy. But most of the environments I've basically met, any massive change to legacy application is simple and no-go. I mean, what I see as the three main technical limitations of the legacy stack I just described. So first one that I see as biggest is distributing events. Many modern apps, so many modern, so to speak, business requirement require like low latency behavior. So instead of executing your code in a polling fashion, you want an event that executes your code. You want to do a business logic as a reaction to an event that happens, right? And this is something where relational databases basically don't have a good answer. There is no natural like API that where you can subscribe for changes, and every time there is a change in legacy application, you basically get this change pushed to your new application. What we want is such an interface. What you can still do with a traditional database is a trigger, which is somehow doable. So you write trigger as a business logic, you deploy the trigger to the database, and every time somebody writes record to the table or updates a record, the trigger gets executed. The issue is the trigger is a part of the write transaction. So if you write a trigger in a way which harms performance, then the writing side, the legacy application, will be affected as well. So this goes against this concept of really minimal changes. So what we usually end up with is doing some kind of polling. So you do SQL query repeatedly every second to check whether there is any change, and then you consider this being an event, which isn't really great. Second issue is that databases are usually rooted in the present. What I mean by that? They usually store just the current snapshot of the application state. So as soon as something changes in the application parses this state to the database, but there is no sense of history, right? And there are cases such as what-if analyses, or generally any trend or pattern detection that simply require a knowledge of the changes, of a history of each record to do that use case. Again, there are some tools that you can use. Actually, SQL 2011 introduced this concept of temporal queries. So you can say select something as of timestamp, and the database gives you a result relevant to the timestamp, which somehow works. But I know that this is a feature implemented in Oracle. It's called flashback queries, I believe. It's in DB too, but I'm not sure whether there is a good support for this in any open source database. If you have better knowledge, I'm more than happy to learn about it. So please just type it into the chat. But I really haven't seen that much used in the practice. So what people mostly end up with is doing some kind of audit tables in their databases so that each record has a timestamp, like valid from valid to. Or what people do is setting another database, which is fine tailored to store this temporal data, and then run an ETL process once in an hour or just after hours to load the data into that OLAP storage or into the temporal storage, which again somehow works. But the issue is that it's not a great fit for fast, kind of real-time applications. If you have to wait for the ETL job to transfer all your data somewhere else, it's not for like online jobs, right? It's something very batch-oriented. So what we are seeing here is kind of impedance mismatch. We have two approaches with conceptual differences, right? We want to build event-driven applications. For those, we need events. But at the same time, what we usually have as data source is legacy applications that are kind of black boxed and that use a relational database. And we want something to bridge this impedance mismatch. And let me come up with a story from the past. I remember that when I was starting with enterprise software as an engineer back in the day, it was the same case with object-oriented programming and relational databases. So people were used to relational databases with tables, and they got objects, right? And objects form graphs, whilst tables form relations. At the same time, objects use references massively. In databases, you don't have anything as references. For object code used composition to build more generalized or specialized structures. In databases, you have like name headers, and it's not really straightforward to map those two. But that created a market for ORM tools such as Hibernate to bridge this gap. And although ORM tools aren't conceptually super clean, there are definitely edge cases that just doesn't work. The practical aspect won. So what I'm suggesting is let's find something similar. Let's find like Hibernate that bridges modern event-driven applications with legacy stacks. And the answer is CDC. CDC stands for Change Data Capture, and it's basically a tool or an architectural pattern that turns your database into the source of event stream. How that works? You basically introduce a new API on the database that is kind of PubSub driven. So your new application subscribes to this API, and then every time any legacy application does an insert or update or delete, this is published as a change, and it gets delivered to all basically subscribers, all consumers. So we get a new API to a database that's read-only, and that's event-driven. How this is actually doable? Under the hood, all major databases contain some kind of lock. It's called bin log in MySQL. It can be also called transaction log, write-ahead log, or operation log, right? Generally, it's a sequence of database operations the database uses internally. So database uses this log for fault tolerance or for replication or for transactional coordination. And the idea here is, okay, if we can somehow connect and extract this internal of the database, then it creates this new event-driven API on the database for us. Just a second. Okay, let me ask, are there any questions of now? Okay, I don't see any. Feel free to use the chat window of WebEx. Just place your questions. All right, how that can work. This brings us to the demo. I have to travel back in time. Maybe 20 years ago, I started playing ice hockey. This is me. In my first hockey gear, I built half of it myself. And we, as a group of enthusiasts, started playing the hockey league. But what we needed was a system for like managing our games and rosters and scores and everything. So I ended up building that. And it's a web application based on LAMP stack. So it's PHP web application using MySQL to store data. So the typical legacy application. And originally, it was very simple. Most database workloads were like transactional workloads. So it was like update one line, such as update player name, or add score, or add game to the game schedule. So that was easy. The page or the application also included stats, but the stats were rather simple, so it was just fine to compute them online. So user clicked on goal leaders, and the app just ran the aggregation on the database and returned the results immediately. That was fine. However, as the system grew, and right now it contains gigabytes of data, this started to be slow. So we introduced overnight stats recomputing. That was still fine because the data were added to the system usually after the game. So it was all like batch oriented, and half day of latency or day of latency wasn't a big deal. that changed pretty quickly when we introduced app for timekeepers. So the lady or the guy who sits in the timekeeper's box and basically stops and starts the clock. Now has an application, and he uses that application to record anything that happens on the ice. So shot, goalie save, period change, time change, penalty, basically everything. And with the real-time data, people started to expect the real-time updates on the website as well. So the stats updated in real time, and also all those changes in stats pushed to their clients in as near real time as possible. So that started to be a bottleneck. And I basically prototyped the solution using a CDC-based solution. So the deployment looks like, or architecture of the prototype looks like this. So I still have my web app with MySQL that's mostly untouched. Then I attached a CDC connector to the database to extract changes, and I wrote a streaming job, so an event-driven analytical job to compute top 10 scorers. And compute that in a real time. So every time there is a change, there is a new goal recorded to MySQL. CDC grabs this information, sends this to a streaming job, and if that goal means change in top 10 scorers, this change is immediately pushed back to subscribed listeners. Let me start the demo, and then I will walk through the deployment, through the components, and then I will go to the code. So there are actually 3 components. The first one is actually my legacy stack, and I have a virtual box with a LAMP stack with MySQL running. So this is something I started in advance. The next thing is a CDC connector with a streaming job. So I will start this from my IDE. Let me start that, and I will compute in the code in a while. So we have MySQL, we have a CDC with a streaming job, and the last part is actually a client. So let me start it as well. This client connects to the streaming job and subscribes for changes. Let's discuss the architecture in a little bit of more detail. Okay, we should see some changes soon, so we'll just wait for the first one. Okay, let's continue. Maybe slow down as I'm sharing my screen. So let's discuss. Okay, we are seeing the first results. Let's discuss a runtime. I will start from a middle. So what's actually a building block of this solution is Hazelcast Jet, which is open source library for stream processing, and this provides us with a clustered runtime for both CDC connector and that streaming job. Nice thing about Jet is that it's just a single Java binary. You saw that I started my code from the IDE. Basically, everything was instantiated from the main method. And this is a really big deal because the only thing I've installed on my laptop before actually running this demo was Java 8. So there are really no runtime dependencies, and this is like really straightforward to deploy. And I think this is also a big deal for legacy applications because if you want to, again, if you are in a legacy environment, then every new kind of system, database, or generally piece of infrastructure that you need to implement and deploy is an extra trouble for you. So we have Jet as a runtime for CDC and a streaming job. To do an actual CDC, Jet uses a project or a library called Debezium. So there is no unified API for a CDC. Right? To approach or to access a database, you usually use SQL as a standard, and all databases implemented. For CDC, there's nothing like that. So using or reading a CDC of a specific database requires some kind of plugging into internals of that specific database. For some databases, that means like using an API to read a transaction log directly. For some databases, and I believe that's the case on MySQL, that means participating in a replication protocol of the database. Some databases, like more modern databases, offer directly a higher level event-driven or streaming API. Anyway, this opens a market for a new tool or new set of tools that do this CDC, do some kind of unification and provide you with a set of connectors. Most of them are proprietary. Fortunately, Debezium is open source and comes with connectors for MySQL, Postgres, Microsoft SQL, and Mongo as of now. There are 3 more, DB2 connector, Cassandra connector, and Oracle connector that are incubating. So yeah, what you need in order to run Debezium is Kafka. So Debezium was basically built as a set Kafka Connect plugins, again, which requires like a Kafka to be installed in your environment. So what we did instead was building a kind of Kafka runtime within Jet that allows you to basically run both the CDC connector, the Debezium-based CDC connector, and your streaming query in one Jet cluster, which is really just JVM running in your environment. So I think that's a lot of convenience. Okay, so that was the middle part, CDC connector part with a streaming job running in a Jet cluster. Now let's go to this MySQL part. Really, all I need to do in my MySQL instance was to allow like full row level logging in a bin log. It was pretty subtle and decent change, which is good because that was our prerequisite. We wanted to use something that's as gentle, as lightweight to the pre-existing legacy infrastructure as possible. So how the CDC part actually works. When the CDC connector opens the connection to the database, to MySQL, it starts by reading a snapshot. So it opens a repeatable read transaction and does a full table scan of the tables you want to subscribe to. So therefore, when I started the demo, it was producing that much data. It was basically doing a full table scan over all goals recorded in my MySQL database. And as soon as it finishes reading of the database, it jumps to this binary log and starts following it. So it does a snapshot and then just follows changes. All right. So this was a big picture. So just to recap the flow, there is a web app creating records to the database. The database writes the records to the internal transaction or binary log. The CDC module running in the Jet cluster can grab each item and push it to the streaming job. The streaming job updates the top 10 and pushes the changes to a client, to the web application. Now, let's have a look to code itself so that you can get a better feel for how one can use it. All right, so what I basically did was starting from this main method. So I start this Jet stream processing runtime in my JVM. I did a little bit of configuration, and then I start the streaming job, and this is the heavy lifting. So let's have a look on how you basically program such a computation. As you can see, it's basically a chain of operations. If you worked with Java util stream, and I believe all of you did, it's very similar. So you basically write or declare how a record should be transformed, and you just chain the steps of the transformation. So in this case, the first step is actually attaching to or using the Debezium connector and attaching to a MySQL database. And then I transform JSON messages to objects, because what Debezium gives you is JSON messages describing the change. Then I'm doing a little bit of data cleaning, and I finally do the aggregation. And the last step is actually sending the results to observable registered in my streaming runtime in Jet. So that when I start the client, which is another JVM, it's completely detached, I can connect to the cluster, register to the same, like observable, and every time, and basically subscribe to all the changes that the streaming computation basically pushes to me. So to see it in action, okay, this is a result of basically the database snapshot, right? Now the streaming job read all the goals in the database, and this is top 5 based on that. And if I go to, this is basically how the application for timekeepers look like. And if I add a goal for the guy who's actually the leading scorer, we can immediately see that it bubbles through the whole pipeline, and the streaming job updates the top 5 and pushes that to the client. This is output, command line output of the client. I'm using Java client just for simplicity. In the real world, you would wrap this by some kind of WebSocket interface so that you can push all the changes to basically some kind of web interface or mobile application. All right. Any other questions? Okay, I don't see any. Again, feel free to use this chat, and I'll answer the questions as they come. Okay. This was saying how CDC is great. What are the limitations? So the first thing is that, okay, the building block of this solution is this operation log or transaction log in the database. But again, for database, that's just something internal. That's not supposed to be a long-term storage. That means that the database internally just keeps a little bit of history, right? Maybe hours or day or two. So it cannot completely replace full log-based or log-based storage such as Kafka. That means that you can't simply replay the complete history of the data, which might be limiting to use cases such as, I don't know, again, detecting patterns over the longer period of time, right? If your database contains just last day of changes, then what you can do is detect such patterns over last day, and that's it. But I think that this is definitely, that the simplicity and the convenience that the CDC tools bring by basically reusing the current infrastructure is definitely worth it. Another disadvantage that I see, it of course adds a little bit of load to your database. We are in the process of testing that for MySQL to start with. I don't think it's going to be tragic, but definitely the database has to log like complete data changes. So this will stress your storage a little bit. So there might be some performance penalty, but I don't reckon it's gonna be more than just a few percent. Okay. So partial conclusions. Where is this good? What are the use cases that fancy this kind of architecture? I think that the first one is materialized views that are offloaded from the DB. Materialized view is something that's in the databases for ages, and it's basically eventual consistent view that's optimized for specific workload. So in database, you can type an SQL query and ask the database to make it materialize. So basically, the database internally will materialize results of that query and keep it updated with new data sheets. CDC with streaming tool and the cache or any database basically is doing the same. It's just offloaded from the database itself. And why is it good? I think that there is no perfect database. For my use case, what I needed was definitely denormalized data. Instead of having one table with players, another table with goals, and then some mapping tables, what I wanted to have was the name of a player, then his total amount of goals, and I wanted to have this ordered to understand who is the best scorer. So it's denormalized data. Relational databases aren't perfect fit for denormalized data. You can do that, but it's not a great fit. Also, what I wanted was this event-driven behavior with pushing changes or pushing updates to the clients. Again, this is something relational databases aren't perfectly good at. And I'm not talking about like deeper analytical processing. The point here is that if you can offload the processing that's not a great fit for the relational database, you can basically, create application that's way more performant, or you can use database that's way better fit for the specific workload. So that is reason number one. And another reason for offloading processing from the database is that I see it's better modularization. With microservices, the trend is that the microservice should also run or own the data that it requires for a full functionality. So if you can like embed the kind of cached data or the offloaded materialized view to the microservice itself, then you are not depending on the master data anymore. You isolate failures. You can scale both parts independently. So you get like looser coupling, which is beneficial for microservice architectures. This is just a simple example where you would basically still use your legacy application as master data store. So all the legacy apps are the master data producers for you, storing the data in a relational database. And you can connect multiple streaming apps that can work with the data as they want. So apart from this real stat service that can be like a machine learning driven prediction service. There can be archivation service that takes all the data, all the changes, and moves them to something like a data warehouse for the new versions of machine learning models, like as a training data. So that's another nice thing about that. And the last but not least, I mentioned scaling, and of course, you can scale even the legacy databases, but it's heavy. It's pretty much heavyweight. Legacy databases usually serve many workloads. That means scaling many moving parts. If you offload just very basic data, there's a lot of changes somewhere else, then you can process it using more focused and more lightweight infrastructure, which is simply cheaper to scale. Just an example. So in my demo, the initial setup was starting one JVM to do the CDC and stream processing, and starting, this was this one, and starting another JVM to basically be a client to listen for changes. If I start another JVM, then in a few seconds, I will start another streaming node. It will discover and join the first guy, and they will form a cluster. This cluster can be good for both like performance scaling, because right now all the players are split to partitions based on the player key, and you basically scale the computation performance-wise this way. And also it works for fault tolerance. So now you are tolerating the failure of one member with no disruption to the service. So yeah, right now, even if okay, now now I have a cluster of two members, and yeah, I can keep interacting with my application. I can keep adding more goals. The client is following that. If I just kill one of the cluster nodes of the stream processing job, the application should just work without an interruption. So you can see that the goals of the top score are just added without any consistent issues. And this is, of course, doable with a relational or like legacy database as well. But I would reckon it's just way more heavyweight process. So lighter tools for lighter jobs. Okay, thanks, Josie, for motivating people to ask questions, but there are still no questions so far. Never mind. Okay, a few practical things related to using Debezium. So Debezium itself, it's Great tool. And again, I think it's the best open source CDC tool available on the market. However, it's still, I would say, raw to be used. What we are trying to do right now is polishing the edges a little bit and make it really convenient to be used in Java, mostly for stream processing in Java. There are 3 areas we focus on. I would like to introduce them, and then I would like to invite you to come up with a feedback. So first thing that we see as possibly limiting is, again, Debezium gives you or is giving you JSONs, basically describing the change that happened in the database. But there is no unification. So you get a different JSON from MySQL and different JSON from Mongo or from Postgres, right? And this is somehow, it's not very convenient. So you have parse it, and you are on your own. So what we try to do is hide this behind object mapping. So what you provide is your Java objects with annotations describing, basically which JSON field would you like to get injected. And then the Jet tooling, the Jet convenience wrapper makes sure that it takes the field from a Mongo database and from a MySQL database in a way that's database specific, but for you as a user, you get the same experience. Another issue is that, for example, when you are getting JSONs from a relational databases, then the JSON message describes the change completely. So for insert, you get a complete payload for the row that's being inserted. But for Mongo, that's different, because for Mongo, you get just something as a patch. So apply this patch, but you have to somewhere take the original document, which also isn't very convenient. So what we are doing is making use of the stateful nature of the streaming environment that we have in Jet. And again, to give this to you as a convenience. So you always get an event object, and you can rely that it contains the full data picture that you need. And it also unifies the operations. For example, MySQL, when it does the initial snapshot, it presents it to you just as insert statements, or insert data. Other databases can basically decide whether, or tell you whether it's an initial snapshot or a regular insert, right? So again, we want to add a layer of convenience to basically unify it as much as possible. This is work in progress. The design document for this effort, for this activity, is available online. And I'd like to basically invite you to give us your feedback, to review that. If this topic is anyhow relevant for you, please reach out to us, and come with your feedback. It would be definitely appreciated. Okay, which brings us to conclusion. So the point here is, even if you are working with the legacy stack, you don't have to rewrite it completely if you want to build event-driven applications. Tools such as CDC are definitely a good means to start with. And consider Hazelcast tooling as you saw in the demos. Okay, cool. That leads us to the last slide. 2 more announcements, or maybe asks. So the first one is that if you are building an application, or if this topic is anyhow interesting to you, please reach out. Again, we are still shaping the feature, so we would appreciate any feedback. And what we are also designing is like 1 hour-long online training, basically build a CDC application from scratch. And again, any feedback would be appreciated. So if you or your team are interested in this topic, it would be really great to get in touch. And we can help you with delivering this training for you, and you can help us with the feedback. So feel free to reach out using my email. So that was the first question, or first announcement. And the other one, this is actually, this talk is or was part of a series of technical talks. Next one, the talk's gonna be about doing machine learning inference at scale. And Marko Topolnik, who's going to lead the session, is going to talk about what challenges data engineers face when building the machine learning pipelines. I'm not sure how many of you actually faced this issue in the past, but what we are seeing is that really the data science teams in organizations are decoupled from the data engineers actually building and productionalizing the data pipelines for machine learning. And Marko is going to talk about some of the challenges and again, the solution that he designed for that. I think that the talk is pretty cool, not just considering the hype around machine learning.
So I guess you must have explained everything perfectly, Vladimir, because no one has any questions. So I just want to thank you, Vladimir, for such a great presentation, and thank everyone for taking the time to join us for the Tech Talk. I will know we had some difficulties for some folks joining or seeing the screen or the audio. So be assured we will be sending out an email with the link to the recording, as well as these links that Vladimir shared on this last screen. And we do hope that you join us next Thursday at this same time for the next Tech Talk, Machine Learning at Scale using Distributed Stream Processing. Our developer community is extremely important to us here at Hazelcast. And since we're living in these times where we can't see each other physically and be in the same room, this was our team's second best option to get you on a place where we could talk with you and share with you. So if you have any suggestions on anything you'd like for us to talk about or things that you would like to discuss, please reach out to us via the Contact Us page on hazelcast.com. I also shared the link in the chat window to next week's talk, so please get in there and register for it. And again, thanks everybody for joining us, and we hope you have a terrific day.